In the last part, we talked about convolutional layers. Let's talk about pooling layers now, which are the other important layer in CNNs. Well, pooling, convolutional, and fully connected layers. But pooling are the other new one, and they're quite a bit simpler, fortunately, than convolutional layers. So they should be pretty intuitive, I think. Yeah, they're only simpler than convolutional layers. So it's a similar idea as a convolutional layer. It just applies the same function to different patches of the input. I'll point out that these do not have any parameters, and they may be a nonlinear function, and you can think of them as a kind of downsampling of the input, which reduce the size. So let me show you a bit more of what I mean. So we're going to just use there's sort of the most common type of thing is a max pool. So let's suppose we have some input which looks something like this. And the idea is that what you can do is apply to this an operation known as a, let's say, I'm just going to do this an example, and then we'll talk a bit more about it. But we'll do what's called a max pool, and we will use a 2x2 filter. That's the size, and we will use stride 2. And that will give us, maybe if you follow, like, you'll know at least these two parts, so you should be able to predict that this will give us a 2x2 output. And the question is, what is each element of this going to be? So like I said, it's a 2x2 filter, so we're going to essentially, the first part we'll look at these four, because it's 2x2, and the question is, what will we put in the corresponding space of the output? Well, if you've been paying attention to the name, you'll see that's a max pool. So it's very simple. You just take the max of this set. That's a 6. That's the biggest number there. Similarly, you can look at the next one right here. And that will map to this one. Recall we're using stride 2. So this is the next set we're going to cover. And you can see here, it's going to be 8. And so on. So here at the bottom left, it's going to be 3, that's the biggest number there, and there's going to be a 4 over here. Let me just really draw them all so that it's 100% clear. This corresponds to this, and finally here I'm gonna give you this. I swear I wasn't paid by Microsoft for this, but okay, so hopefully it's a fairly intuitive idea. And like I said, there are some hyperparameters here. So the hyperparameters here are like the filter size and the stride. So 2 hyperparameters. And I mean hyperparameters in the sense that you will have to select these when you design your pooling layer. What you do not have to decide is things like the padding. We don't generally use padding for these types of things, and you don't have to specify the number of filters, in the sense that usually when we do a pooling layer, you apply it independently to each channel. So essentially, each channel of the input becomes a new channel of the output, and it's sort of entered layer-wise. And there's a few different pooling operations that are used. So there's max pool, which is very clear. It essentially takes the max of each element of the elements which are within the filter. There's also things like average pool. So maybe you can figure what that is. It'll just average the 4 things that are, whatever things are in the filter size. You can actually see this as a previous convolution. It just has fixed weights instead of trying to learn those weights itself. And then there's also, say, L2 norm pool. Yeah, so these are different common types of pooling operations. And yeah, the crucial differences from the convolutional layer is that there are no parameters, only hyperparameters, but there's no learnable parameters. Let me put that here, no learnable parameters. And the fact that you only ever have one filter for it, in which you apply independently to the different layers, the different channels. Only one filter. Yeah, so that's about it. Let me try to summarize. It's a pretty intuitive idea, I think, and much simpler than convolutional layers. So let's summarize pools and talk about some of the maybe the same calculations that we had. So we have an input, which is of size W1 by H1 by D1. There's two hyperparams. Which are the width / height, which are F. There is the stride S. And like I said, there's no padding or multiple filters. Those don't really make sense. In this setting, the output will be of size W2 by H2 by D2. And for this, we have W2 equals W1 minus F over S plus 1. This is basically the same calculation as we did before, except we don't have any zero padding this time. Similarly, H2 is equal to H1 minus F divided by S plus 1. And the important difference here is D2, which is just going to be equal to D1. Like I said, we apply the filter, the pool operation independently to each channel, and they sort of map up one-to-one. Okay, and how many parameters are there in a pooling layer? Well, it's a trick question. There's no parameters. Like I already said this, but no learnable parameters. So that's a very quick summary of pools. They're simple. Okay, so what does a CNN look like? Let's try to put this all together and understand what a CNN structure may appear like. So it generally has the following type of picture. First of all, we're going to have the input. That will be fed into something that looks like a bunch of conv plus, say, ReLU. I'm going to use ReLU here because that's the most common activation, but it's just any sort of activation function. So yeah, we feed into conv layers where we're going to do conv, and then you apply this nonlinear activation to each output, and then we can repeat this a bunch of times. Say you just feed into another one and another one, and then after a bunch of those, maybe you'd feed it into a pool. And then you could also repeat this whole structure here. Since you may have conv ReLU pool, conv ReLU pool, conv ReLU pool, or maybe you have conv ReLU, conv ReLU, conv ReLU pool, conv ReLU, conv ReLU, conv ReLU pool. And then, yeah, after a bunch of these, then you'd maybe have, you'd start going into some, once you've really gotten towards the end of the network, you'd start going into fully connected layers. Maybe, and then maybe repeat. And then finally, towards the very end of this, you would have, say, fully connected into a softmax. And the softmax, like I said, is at the end, which would convert your last fully connected layer into some logits or like some probabilities where you basically pick the max one in terms of doing your classification task. So yeah, that's roughly what the structure is, and we'll see some examples about this in a sec on what exactly a neural network structure, like what realistic ones look like. I'll mention also that generally we start off with say bigger images, which have like, say, like in the example we mentioned earlier today, it was say 227 by 227 by 3. So you can see that these have big width and height comparatively and small number of channels. But as we proceed in the network, we're going to go down and we're going to have fewer, it'll end up being, you'll see in the example that we'll get to a bit later, I think, but it'll have fewer and fewer width, less and less width and height, but more and more depth and more channels. And that's kind of natural with what happens, as you maybe saw in the examples, because you can only really reduce the size unless you use zero padding, but you can only really reduce the size of the input when you put in a convolutional layer. It'll become smaller and smaller. But you can always make more different channels by just adding more filters at a given layer. Good. So that's what the structure for neural networks look like, and we'll see in a sec some of the key important structures in convolutional neural networks, which have been some of the most important in the history of neural networks, which is really over the last decade, because they've been some of the ones which really work the best and have made important proof of concepts for the field of neural networks. So let's see some. Before we get to that, though, I want to show you some of the basic data sets, because really machine learning wouldn't be where it is without very good data sets to work on, because how else would we know if an image classifier is a good one? So we need data sets. So the first one I'll bring up is MNIST, which I'm sure we've already talked about before a few times, but let me just remind you in comparison to some of the other ones. So MNIST is kind of one of the simplest data sets that we have in image recognition. It's a set of images which are 0 through 9. There's like 60K training images. There are 10K test images. There are 10 classes, one for each digit from 0 through 9. The images are, in terms of their size, they're 28 by 28 by 1. The 1 is because they're black and white. And this is a very easy data set. It's kind of, we don't really put much stock in a neural network if it's only, or some sort of machine learning result, if it's only proved on MNIST. Most, even very simple classifiers can get like 99.9% accuracy on this. It's very, very easy. But it's a good thing to try just to make sure, as a sanity check, to make sure something isn't totally broken or doesn't make any sense at all. So MNIST is very easy. Perhaps the next harder one is something known as CFAR 10, which is the CFAR actually here stands for the Canadian connection, the Canadian Institute for Advanced Research, maybe, I think something like that. But yeah, it's a Canadian institution. CFAR 10 is what it's named, and it's called CFAR 10 for that. And there's 10 classes similar to MNIST, but rather than for MNIST, where it's the digits 0 through 9, you can see that these are much more challenging classes. You can see, yeah, it's a bit hard to zoom in here, but you can see, for example, the classes are more exciting things like cars and birds and cats, dogs, frogs, horses, and so on. So yeah, it's a bit hard to like really see the images, which is actually a common complaint about this data set, in the sense that it's hard for even humans looking at these to figure out what these things are sometimes. They're very blurry. And they are blurry because these are actually fairly low resolution images. They're 32 by 32 by 3 this time. You can see they're color images. So they're fairly small images, barely larger than the CFAR, the MNIST images. The dataset size is actually smaller than before, which is perhaps surprising because, or at least it makes it challenging because of the fact that this is clearly a harder task. So there's 10K or 50K train, 10K test, and 10 classes. And this is, yeah, you can clearly see hopefully that this is a much more challenging task, because for a 0, you know, most people draw their zeros in the same way. You'll see like these white pixels in the same types of areas. So, but on the other hand, dogs do not all look alike. If you just look at the dog row, they're all very, very different looking pictures compared to how you'd see zeros and ones and stuff. But so yeah, this makes it a significantly more challenging than MNIST. Nonetheless, this is harder, but it's mostly solved by modern neural networks, which can still get, say, 99% plus on this data set, which is kind of, I think, pretty impressive. It's not obvious that even, say, a human could do that. Yeah. But both of these are kind of easy in comparison to the real sort of proof, like really where neural networks have proved their value, which is in what is known as ImageNet. So ImageNet is actually a huge data set. It's a massive data set, and most of it is not used for this type of purposes, but it's something like 14 million images. These are of varying sizes. There's something like 400 by 500 or something. Like they're not all the same size. So there's something like that, and they're of course by 3, something like this. That's their size, and you can see this is much bigger than the previous images. And there are actually tens of thousands of classes. So you can see in all 3 numbers here, more classes, bigger images, a lot more images. This is a much harder data set. Let me just show you an example of what some of these pictures look like. I have some right here. So you can see here that these are much higher resolution images. I've shrunk them just because I don't want to take up the whole page, but you can see that these are much higher resolution. They're much more varied in terms of what they are. There's going to be many different classes. For example, you might classify all these things at the bottom right as various types of dogs, but actually they have distinct and different labels, just different labels for each of them. They're different breeds of dogs. I bet I know I can't name most of them. So yeah, but there are different labels which image classifier is expected to, perhaps. So this is like the whole image net, which is typically not used in neural networks as is. Instead, what is used instead is what is known as the ILSVRC dataset. Maybe, like, to be precise, the 2012 to 2017 dataset or something like that. Which this stands for, like, I'm gonna butcher this, but it's something like Image Learning Large Scale Vision Recognition Competition. I don't know. The point is, it was an annual competition that would run for a long time, and the question is every year, who can come up with the best image classifier? Who can do the best on some particular image classification task? And the winner, it gets eternal fame and glory. I say this a bit sarcastically, but it actually is perhaps true, and we'll get to that in a little bit. But yeah, this data set is kind of a bunch of these, is a subset of ImageNet, and the size of this is still large. It's not as big as before, but it's 1.2 million training points. And it consists of in the version that people generally used, it has a 50K point test set, and it consists of 1,000 classes. So you can see still, even despite the fact that we shrunk it down, this is still a lot harder in terms of the size, number of classes. The images are, of course, the same size because we didn't shrink them. But yeah, this is a very challenging task, and if you can do well on ImageNet, then that's pretty meaningful. And progress on this ImageNet data set is one of the things which really pushed the state of machine learning, as we'll talk about in a second. So yeah, there's many more data sets besides just these 3, MNIST, CFAR10, ImageNet, but these are at least 3 of the common ones which you really should know if you're working in machine learning. So those are just the ones I'll name drop now. Okay, so with that out of the way, those architectures, or sorry, those data sets, let's talk about some of the classic architectures within convolutional neural networks and see how things have evolved over time. So one of the first ones is something known as, this is called Lynette. Maybe Lynette 5, but this is from, say, 1998. Maybe even older than that, depending on how you count, but this is a relatively small neural network, which was in a paper by Lynette et al. That's where kind of like the name comes from, Lynette, I guess. And this was made basically to work on, okay, for this one it says input 32 by 32, but it was basically meant to work on, say, MNIST style things. And in fact, this algorithm itself, this neural network, was used, maybe it still is used, I'm not sure. It was used for a long time in check recognition. When you deposit a check, it somehow figures out how much you deposited. Well, it was basically doing using neural networks at some point in the past, at least, which are based on this architecture in many different places. So yeah, let's talk a little bit about this architecture. And in fact, I have it sort of written out here. This is from Wikipedia. Let me shrink this down a bit so that we can see it. Yeah, so this is the architecture. Let me just overlay it, in fact. And you can see that it's okay. It's like a reasonable sized network. It's nothing too big, but it's something that's, I guess, a bit interesting. So we start with the input is 28 by 28 by 1, which is just the an MNIST image, let's say. And what we do is first a convolution with a 5 by 5 kernel, 2 padding, and 6 different kernels. And so that'll give us this layer here. What we then do is we do pooling with a 2 by 2 average kernel, 2 stride, and so on. So we use so first we have a conv layer, then we have a pooling layer, sometimes called subsampling. Then again, we have a conv and pool. So you can see this pictorially here. Here we conv it. This is going to be a conv, and this is going to be a pool. And so then after this, what we do is just a bunch of different fully connected things. So here, at this point, we transition from like I said, in any sort of, in many types of neural network convnet settings, what we do is we have conv pool, and then eventually we get down to fully connected layers. So what we do when we reach the last layer of this conv pool segment is going to be that we flatten it. We basically take all these filters we have, which are, there's 16, which are each 5 by 5. You can see that they've become very small, but there's many of them. What we do is we just sort of flatten them. So we take this 16 by, we make this into one long vector, which is of size 16 by 5 by 5. And then we connect it to a layer with 120 neurons. And then we do another fully connected layer with 84 neurons. And then we do a, basically, yeah, another layer connected to a 10 by, a length 10 vector. And that'll basically be our output. You can take a soft max of that or something. So you can see, and okay, one more thing I'll mention inside of this is that there's always going to be activation functions which aren't really, which aren't explicitly pointed out here, but they are in this. For example, it points out these sigmoids and stuff. So yeah, this is a fairly small network in the sense it only has 2 convolutional layers. And yeah, it's reasonable. There's some sort of archaic things which aren't really seen in modern neural networks anymore. For example, this uses the sigmoid activation, or I've seen some places say sigmoid, some places say tanh. It's not really a big deal. The point is both aren't really used anymore. Yeah, that's the main thing. It also uses average pooling. These are average pool layers, which are somewhat less used compared to nowadays. Max pooling is more popular. But yeah, this was rather comparatively old as the field goes, architecture, and it did pretty well at what it was supposed to do. That said, neural networks weren't the most popular for a long time, and because it seemed like other approaches could do a lot better for more challenging tasks. But eventually came along what is known as LexNet in 2012, and this was really when the start of some will say the start of the deep learning era has begun, just because after this sparked so much excitement and interest based on the results that were here. So let me compare this with here's another picture, which is the LexNet. So this is a bit bigger. It's not actually that much bigger, but than Lynette. Let me just put them next to each other. So yeah, you can see LexNet compared to Lynette. It's like a little bit bigger. You can see it's got, what are the differences versus Lynette? You can see that here it has, say, 5 convolutional layers instead of just 2. That's kind of it, I guess. There's a few, there's an additional pooling layer somewhere, a few more neurons. Each of these layers are wider. I mean, okay, the reason why these numbers are bigger is because of the fact that you can see that these are, if you're paying attention during the datasets part, you can see that this takes an MNIST based on the size here, but this is much bigger, and LexNet was really meant to do, it was designed to do well at ImageNet. And in particular, the big deal about LexNet is that it did really well on the ImageNet, or what is it called, the ILSVRC competition in 2012. In fact, it blew the competition out of the water. It beat the competition by 10% in terms of the accuracy. in ILSVRC 2012 by a huge margin. I think it was something like it had a top 5 error of about 15% versus 25% for best alternative. So you can see that what is top 5 error? It says, so each image has a correct label. What top 5 error means that if you take a look at the network's outputs and see what which are the top 5 things it thinks the image could be, then if any of those 5 is accurate, then it gets it correct. Otherwise, it's wrong. So you can see this is still a fairly challenging task because there's 1,000 different output classes. So get a top 5 error of 15% is quite impressive. So this is like 85% accuracy versus 75% accuracy for the best. So this was really when people opened their eyes to see how effective neural networks could be at these types of very complicated and complex tasks. So while I said it doesn't seem that different just when you put them like this, it was actually quite an engineering feat. There were a number of things which innovated here. One thing, for example, was the ReLU, which is like we already know and love, and it's kind of very common now, but this was a new thing at the time, relatively. Other things like, for example, it used max pooling instead of average pooling. They used a lot of data augmentation. They used dropout, as you can see. There's dropout in certain layers, the fully connected layers. This was trained using SGD with momentum. And perhaps the interesting thing is nowadays there's a very mature and rich architecture, or like there's a lot of tools if you want to do machine learning now. In particular, if you want to train neural networks on your GPU, because training on a GPU is much, much faster than training on a CPU because of natural parallelism in neural network training. You can do this via fairly simple tools from GPU manufacturers, like NVIDIA, for example, makes some nice software which is useful for activating the power of your GPU, combined with modern neural network frameworks, which can really do these things work together really well to use GPUs very efficiently. Back in 2012 was an eon ago in neural network times, and none of this really existed. So they actually were having issues because of the fact that their data set, their data was too big to fit into just one GPU. So they had to do some crazy engineering stuff where they split it over 2 different GPUs and had them talk to each other. And they had to do this all by themselves. Like implementing that back then would be a nightmare. Nowadays, no problem. You could probably do it yourself if you wanted. You can't really do it quickly on your own personal computer, maybe, depending on what type of GPU you have. But yeah, it was really a nightmare and not something I would personally want to do back in the day. But yeah, this is what really kicked off the modern interest in neural networks. So the next network that we want to talk about is something called VGGNet, which was 2014. You'll see that the progress gets to be a lot faster. The previous gap was 1998 to 2012, but now 2014, and all of these other ones fall into a certain same type of narrow. Let me put this on the next page, I guess. So yeah, VGGNet, let's maybe zoom out a bit. These are starting, as you can see, the point is that these are starting to get deeper. So let me just talk about this, I guess. Yeah, you can see here on the left is LexNet. And on the right here are 2 different variants of VGGNet, which you can see 16 and 19, depending on how deep they are. And you can see that the main difference is, there's kind of 2 main differences here. One is the fact that it's deeper. These 2 differences go hand in hand, actually. One is that, obviously, you can see by the picture, it's deeper. This is maybe twice as deep. There's twice as many layers. The other difference is a bit hard to see because you have to look very carefully. But notice here that LexNet has bigger convolutions. You can see here it has, say, an 11 by 11 convolution, and then this layer here is 5 by 5. Whereas if you look carefully, all of these are actually going to be 3 by 3. And why is that? Well, like I said, these go hand in hand because of the fact that essentially you can simulate these kind of 5 by 5 convolutions by just having more layers of 3 by 3 convolutions, and so on. 11 by 11 can also be simulated by more layers as well. So let me show you what I mean by that. So let's suppose here's an output image, or an output layer, and there's like a 1 by 1 pixel here. Well, what you can imagine in the previous layer, what it might have been if you have the 3 by 3 filters, this is here that corresponds to a 3 by 3 patch. And if you go another layer back, well, each of these pixels in this one was caused by a 3 by 3 patch, and there's a 3 by 3 grid of them. So going backwards, you can see that this is a 5 by 5 patch here. So kind of this 2 layers from now was kind of computed as a result of a 5 by 5 patch here. So that's sort of, in some sense, equivalent to if you just had a 1 5 by 5 layer, which kind of just went straight from the first one to the third one. But let's say that doing 2 layers with smaller filters is more parameter efficient than 1 layer with a larger filter. So let me sort of summarize that. More layers plus small filters. This is better than few layers plus large filters. And that's kind of the idea. And why is it better? Is because it turns out to be more parameter efficient if you do the calculations. So yeah, this is kind of one of the ideas, and having fewer smaller convolutions let you stack it a lot deeper, which turns out to give a better accuracy. So yeah, maybe one way of referring to this is like the receptive field. So the receptive field of this is kind of the same if you use 3 by 3 filters and 2 layers versus 1 layer and 5 by 5 filters. Cool. So we're getting towards a little bit closer to modern day, I guess. We're only going to stop at 2015, so we're not going to get that close. But there's 2 more architectures I want to talk to you about. One is VGGNet. It's kind of a pun on Google and Lynette. But yeah, this is where it starts getting kind of ridiculously deep in terms of the number of layers, and you'll see why in a second. It is based around this core inception module, as it's called. So this is kind of just like it's like just a set of basically a description of a layer, or a few different layers that we put together in order to make a little bit of to make a little module. And the nice thing about neural networks is you can make layers and you can stack them, you can make modules and you can stack them, and build a neural network very modularly. So this is what is known as the inception module. And you can see that sometimes it's not clear what size of convolutions you'll do. So what you do instead is you just try them all. So what you do first of all is, given some input, what you can do is do a 1 by 1 convolution, and in parallel you do 3 by 3 convolution, 5 by 5 convolution, and you do pooling, and then this will give you a bunch of different layers right here. What you can do is just concatenate them all together. So you just stick them together all into sort of one layer, and then you can go from there. So yeah, this is just kind of throwing the kitchen sink at it, just trying a bunch of different convolutions and seeing what works. Another thing which is done in practice is also like inception module with dimension reductions. So what you can, this kind of, I'm not going to get too much into the details here, but you can see here that instead of just doing a 1 by 1 convolution, or a 3 by 3 convolution, first we do a 1 by 1 convolution before it. So if you think about what this 1 by 1 convolution does, is it essentially takes all, imagine you have a W by H by D input. Well, what a 1 by 1 convolution would do is collapse that. If you have, okay, basically, sorry, let me write this a little bit. If you have a WH by H by D input, if you have K filters which are 1 by 1, then this will give you a W by H by K output. So yeah, it's a very simple type of convolution, but it can be useful in terms of dimension reduction, in the sense if K is much smaller than D, then it'll make future computations a bit easier in terms of having fewer parameters, which is a good thing if we can, as long as we maintain the same capacity as before. But so yeah, this is sometimes done as a dimension reduction type of technique, as it's called. But yeah, you essentially just try a bunch of different convolutions and see what happens. So this is the inception module. Pretty simple, right? It's not too big. It's nothing crazy. But how do you use this in a neural network? Well, let me show you what the Google Net looks like. It looks something like this. Yeah, this is a monstrosity. It's huge. This is a figure from their paper, and you can see I'm not even going to try to read these out, but you can see it has many more layers than anything else we've looked at so far. You might recognize, if you sort of squint at it, this picture here on the right. Notice how it looks kind of similar to this little thing here. So there's an inception module right here, each of these little things here, and this is an inception module, and so on. It's just basically stacking, I don't know, like 8 or 9 of these things in a row, and then you get a classification. Yeah, so that's, you can see this is really getting to the ridiculously deep point, and this was also in 2014, so not too long after LexNet. Okay, one thing I'll note here is that's interesting. At the end, we don't really have any fully connected layers because those introduce a lot of parameters. Instead, what is done is we simply use an average pool, which, yeah, an average pool is one way of getting the, as long as, yeah, somehow an average pool seems to be the right type of thing to do, and it doesn't have as many parameters as a fully connected layer in terms of getting down to just final levels, which we can take a softmax out of. So yeah, that was one innovation there. And okay, time for the very last thing I want to tell you about in this rather long lecture, and that is residual networks, or ResNets, which were something around 2015. And this one is not really all about trying to make the network, okay, it does involve making the network bigger, but there's a very interesting innovation in this type of network, and it's the idea of residual connections. So here is a interesting plot from the ResNet paper by He et al. And you can see that here is the performance of 2 different neural networks that they trained. So this is the training error on the y-axis, and this was the number of iterations. And you can see the yellow line here. This is a 20-layer network, so a smaller network. And you can see the training error is much lower than this red line here, which is a 56-layer network. So this is confusing because everything we've talked about so far is the fact that we've made these networks bigger and bigger, and I guess we haven't really seen it, but you can maybe believe me that as we make them bigger and bigger, they become better and better. Yet, however, the challenge is the fact that the oddity here is the fact that as things become bigger here, perhaps the training error doesn't go down. In fact, you can see the training error is bigger here for a deeper network. So what's going wrong here? The thing that's going wrong here is the fact that deeper networks are actually more challenging to optimize. That is, there's more layers. So I'm not going to get into all the things like vanishing gradients and exploding gradients, and these can be issues depending on your activation, and just in general, it's more challenging to optimize when you have a deeper network. Like this is why people don't just set networks to be like 10,000 layers deep, because it's going to be very difficult to optimize and you run into issues. And I guess one thing, the sort of key innovation for this ResNet architecture is they try to make sure things don't have to go through so many layers in order to get the signals where they need to be. So this is a bit abstract, but let me show you kind of what the key ResNet block is. It's going to be something like this. So I'm going to start off with something which is fairly familiar to you. 3x3 conv, and then we have, say, ReLU And then we have maybe another 3x3 conv. And then we have another ReLU. And we go on to the next layer, ... Okay, so this is pretty familiar, maybe what you've seen before. But what we're going to do instead is we are going to have what's known as a residual connection, a skip connection, a highway, shortcut. I don't know. I've heard a few different names for it. But basically, what we're going to do is take the input here, and we're going to add it on here. So this is called a residual connection, I guess, or I guess that's, yeah, what it can be called. And the idea is the following, because here we had this 56-layer network, and to get to like the later layers in this 56-layer network thing, the signal from the start would have to go all the way through 56 layers. And when you go through that many layers and you take that many derivatives, then somehow some of the signal starts to get lost. So what this does is it allows some of the signal to just basically skip through some of these layers so it can get through easier, which helps a lot with optimization. And yeah, essentially it allows also, yeah, I guess one way maybe you can see it is you can essentially simulate a neural network with fewer layers, even if it has more layers. So it shouldn't really do worse if you think about it in a certain way. And yeah, this residual idea has been influential and it can be very useful in a lot of settings. Okay, so that's it. This was a long lecture, but we now know a lot of things about convolutional neural networks. And yeah, they're an important concept which have been very influential in the field of neural networks, which have fueled a lot of growth over the last decade or so.